Hi, good to see you.
Okay, welcome back everyone to the morning session. So we're delighted to have Lea Bottini from Oxford, who's going to speak to us about gapped phases and phase transitions with categorical symmetries.
Okay, thank you. And yes, today I'm going to talk about this work, which is in collaboration with people in Oxford, Laksha, Daniel, and Sakura, and Apur, which is in Copenhagen. And sort of the framework in which we're working is this modern perspective of symmetries that was introduced in this seminal paper in 2014, and it's the idea that we should really think of symmetries as associated to topological defects in a theory. And in my talk, I'm going to work strictly in 1+1D dimensions, which means that for me, a global symmetry S will be associated to topological line defects in the theory. And the structure that we expect to describe these topological line defects is a fusion category, which I will also call the symmetry category of the theory. So it's a fusion category because it has objects that correspond to topological lines. It has morphisms that correspond to local operators that sit at junction between two lines. And then we have a fusion structure that includes standard group-like fusion, but also generalizes to a more general fusion algebra. And here I put a non-exhaustive list of works that deal with fusion category symmetries in 2 dimensions. So in particular, our starting point is the very well-known Landau's paradigm. So the idea that we can characterize continuous phase transition, second-order phase transition, as spontaneous symmetry breaking phase transitions. So we have a theory with a symmetry S, and let's say that this symmetry is spontaneously broken in some phase 1, while it's preserved in some other phase. And then we know that there is a CFT that sits at the transition between these 2 phases. And moreover, we can characterize phases in terms of order parameters. So an operator O that is charged under the symmetry and that acquires a non-zero expectation value in some order phase where the symmetry is spontaneously broken, and it has 0 VAV in a disordered phase where the symmetry is unbroken. So our goal will be to generalize this picture to the case where S is not a standard vanilla group-like symmetry, but a symmetry described by a fusion category. And 2 disclaimers are that, as I was saying, I will only work in 2 dimensions, and that for me S will always be a finite symmetry, which in particular means that the IR phases for when we spontaneously break these symmetries are gapped and there are no Goldstone bosons. Okay, so the plan is that I will explain this general framework and also show how we can actually realize this in some lattice models. And first I will review the classification of gapped phases and phase transition using the SymTFT. And here I also put some works that work on related topics using the symmetry TFT or symmetry topological order. Then I will show an anion chain realization, and also how in some instances we can use standard spin chains, and then I will conclude. And also here there are some related works for anion chains and spin chains. And the main example that I will use is going to be RAPS3 throughout the whole talk. Okay, so as I was saying, the key tool is the SymTFT. And the SymTFT is something that takes as input a 2D QFT that has symmetry S and constructs a 3-dimensional topological theory. And the topological lines in this theory, I will also call them anions interchangeably. They form the modular tensor category, which is the Drinfeld center of S. And the idea is that this admits 2 boundaries, a symmetry boundary, which is topological, and a non-topological boundary that encodes all the dynamics of the theory. And the symmetry boundary has the property that the topological lines that live on it reconstruct my fusion category as describing the symmetry. And then my original theory T can be recovered as the interval compactification of the SymTFT. So this is the sandwich construction. So in this framework, how do we characterize charged operators? Well, they come from an anion Q in the Dreamfield center that stretches between the symmetry boundary and the physical boundary. In particular, this has to end completely on the physical boundary, and then when I take the sandwich, I get an operator. This may or may not be attached to a symmetry line, depending on whether this ends completely or doesn't end on the symmetry boundary. And then this fact that the operator is charged under the symmetry comes from the fact that this anion Q and, say, another anion S braid non-trivially in the bulk. If we assume that S is one of those anions that when I push them to the symmetry boundary become a symmetry generator. Okay. And the final thing that we need is concretely how we specify a gap boundary condition of the SymTFT. And it turns out the gap boundary conditions are in one-to-one correspondence with Lagrangian algebras in the Dreamfield center. And a Lagrangian algebra is essentially a sum of anion in the SymTFT. And it is the maximal set of anions that can terminate on a boundary. So anions that belong to L to the Lagrangian algebra can completely end, while the anions that don't belong to the Lagrangian algebra do not become trivialized on the symmetry boundary, they continue, and they become the symmetry generators. Okay. So our idea to classify gapped phases with symmetry S in 1+1D is that we start with our symmetry S of interest and we construct the Dreamfield center. And then we need to classify all possible gap boundary conditions. And so this amounts to classifying all possible Lagrangian algebras in the Dreamfield center. And then since we want to study S-symmetric phases, we need to fix the symmetry boundary. In particular, among all of these Lagrangian algebras, there is going to be one that I called LS, which is the one that realizes the symmetry S on the boundary, and I fix this. And then normally the right boundary, the physical boundary, has nothing to do with Lagrangian algebras because it's a non-topological boundary conditions. But here we want to study TQFTs. And so in this case, we also need to pick the physical boundary to be topological. So also the physical boundary for me is going to be specified by some Lagrangian algebra, which I called L-phys in the Dreamfield center. And this guarantees that when I take this sandwich, I actually get a TQFT. And then the idea is that by fixing LS on the left and by cycling through all the possible L-phys on the right, I will span all possible asymmetric TQFTs. So in this way, we can also define, for example, generalized order parameters, so operators that are charged under the symmetry and that acquire a VEV in the phase. And if you recall, charged operators are specified by things that can completely end on the physical boundary. So this means that they are specified by anions that belong to the physical Lagrangian. Then we can also, for example, obtain immediately the number of vacua. These are anions that completely end on both the symmetry and the physical boundary, because these give rise to topological operators genuine in the TQFT. And using this picture, we can also very concretely determine the symmetry as on the vacua, so the full pattern of spontaneous symmetry breaking. So let's do an example, RepS3. So this is the fusion category formed by reducible representation of the permutation group of 3 elements, which I denote in this way. A is a Z3 subsymmetry, and it's a cyclic permutation. B is a Z2 subsymmetry, and it's a transposition. And then the non-commutativity is encoded in this relation. BAB is A squared. And S3 has irreducible representation, a trivial one, a one-dimensional representation that I call P, which essentially counts the number of transposition, and a two-dimensionally rep E, which is the fundamental representation of S3. And these are the non-trivial fusion rules. In particular, notice that E is non-invertible, while P generates a Z2 subsymmetry. And it turns out that there are 4 possible Lagrangian algebras in the Dreamfield center of RepS3. So there are 4 gap boundaries, And from our framework, we know that there are going to be 4 gapped phases with Rep-S3 symmetry. And what we find is that there is a trivial phase with a single vacuum, which is trivially Rep-S3 symmetric, a phase with 2 vacua that are exchanged by the generator P of the Z2 subsymmetry. So we call this a Z2 SSB phase. And then there are 2 phases, both with 3 vacua. One in which the vacua are exchanged by E, but are left invariant by P. So we call this a Rep-S3 mod Z2 SSB phase because Z2 is preserved. And then a phase where the full Rep-S3 symmetry is spontaneously broken. And using this SymTFT framework, we can also characterize some phase transitions between these symmetries. And the idea is that we want to extend the standard SymTFT picture, so the standard sandwich, with the addition of another gapped interface. And this gapped interface in particular is specified by a condensable algebra in the Drinfeld center, which is non-Lagrangian, so non-maximal. In particular, a Lagrangian algebra specifies a gapped boundary, but if you take a non-maximal algebra, then there are anyons in the original topological order that still break trivially with some of the anyons in the algebra A, so they survive the condensation process, which means that we get actually an interface to a reduced topological order. This reduced topological order is Z of S mod A, and we can re-express it as the Drinfeld center of another symmetry, S prime, which is in general a smaller symmetry than S. And the idea is that we then consider this picture that we call the club sandwich, where we have the symmetry boundary, our Drinfeld center of S, this interface specified by the algebra, and then this center of a smaller symmetry S prime. And then we can close it with a physical boundary, which in general, using the standard SymTFT philosophy, is a boundary condition for a QFT with S prime symmetry. But by taking this full sandwich, we actually get a TQFT that has the full S symmetry. So, like very concretely, we can think of this club sandwich as a machinery that takes as input an S symmetric QFT, and it outputs S prime symmetric QFT, and it outputs an S symmetric QFT. And why this is relevant for phase transitions? Well, because assume that we know a CFT C prime that sits at the transition between 2 S prime symmetric phases. So it admits a relevant deformation by an operator epsilon prime that goes to phases, let's say T1 prime, T2 prime. And if we input this CFT C prime as the physical boundary condition in this club sandwich, then we can use this to map it to now an S-symmetric CFT that sits at the transition between 2 S-symmetric phases. So this is sort of a way of generating new phase transition, once you know phase transition for a minimal small S prime symmetry. And let me go back to the Rep-S3 example. And suppose that I want to know the phase transition between the two phases that have 3 vacua. So the Rep-S3 mod Z2 SSB phase and the phase where I fully break Rep-S3 symmetry. And if you do this club sandwich construction, it turns out that the reduced topological order in this case is the toric code, so the Drinfeld center of Z2, which means that in this case the reduced symmetry S prime is actually Z2. And using this philosophy, we can now input a Z2 symmetric CFT, which is, for example, the Ising CFT, and using this construction, sandwich it to a Rep-S3 symmetric CFT. And what we find is that the CFT at this phase transition is made up of 2 universes. Each universe is a copy of the Ising CFT. And these 2 universes are decoupled dynamically, but they are coupled in a non-trivial way, the action of the full Rep-S3 symmetry. So in a sense, it's like having an Ising CFT, but stacked with a Z2 SSB TQFT on top of it. Okay, and now let me move to lattice models. And the idea is that we want to construct 1+1D lattice models that flow to these gapped and gapless phases that we described abstractly using the SIMPFT, and that have action of a fusion category symmetry S. And a very natural thing to look at is anion chains, because these are models that are naturally defined with the action of a, they are built in basically with the action of a fusion category symmetry. And for me, the data that is going to enter the definition of this anion chain is an input fusion category C. This is in general different from the symmetry I'm interested in. Then we pick a C module category M, and then an object in the input fusion category, which is in general a non-simple object. And then the symmetry S of my model is obtained as the dual symmetry of C with respect to the module category M. And the state space of the model is going to be spanned by fusion trees of this type, where the horizontal edges are labeled by elements in the module category, and vertical edges are labeled by rho. And the symmetry S acts from below, so I can take a line S in this fusion category and just smash it on this edge here. And notice that this action is consistent because this C module category M is naturally a left C module category, but a right C dual M module category. So I can take this line and consistently fuse it here. And then the claim is that we can construct gapped Hamiltonians whose ground states realize each of the gapped phases with symmetry S that I described with the SIMPFT. And the Hamiltonian operators are constructed in this way. So they have this shape that we glue on top of the fusion trees. And now the crucial point is that if I want Hamiltonians, our claim is that you need to specify these edges to be labeled by an algebra object in the input fusion category. So again, let me go back to the RepS3 example. In this case, I take as input fusion category S3, and then I take as module category the module category labeled by Z2B, so the subgroup generated by B in S3. And the simple objects in this module category corresponds to B cosets. So I have 1 that corresponds to 1B, M that corresponds to AAB, and M squared that corresponds to A square B. And I take rho to be the sum of all elements in S3. And in this case, C dual M turns out to be RepS3. And this corresponds to the fact that I can actually obtain RepS3 by gauging the non-normal Z2 subgroup in S3. And now let's look at the state space of this model. This is going to be spanned by these fusion trees, where these horizontal edges, again, is labeled by an element in the module category. So, for example, M squared. And vertical edges is labeled by elements here in rho. And notice that actually the state space turns out to be tensor product decomposable into C3 at integer sites. And C3 just depends if I pick 1M or M squared. But notice that in this morphism space here, I actually have always 2 possibilities. For example, if I have M and I want to go to M squared, I can select A, because A times AAB gives A square B. I could also select B, because BA is A square B, and then BAB is A square. So actually, I also have C2 here at these alpha integer sites, and this tells me the possible morphism that I pick to span this fusion tree. So actually, in this case, this onion chain turns out to be the total space decomposes into tensor product of C3 at integer site and C2 at half integer sites. And I will then basis state in this way, where P can be 0, 1, 2, depending if I pick 1M or M squared, as I was saying. And Q at half integer sites can be 0 or 1, where essentially I use this map that tells me if I pick the morphism corresponding to selecting an element that doesn't contain the B or doesn't contain the B in S3. And now we saw that there were 4 possible gapped phases in RepS3. And indeed, there are 4 gapped Hamiltonians that, as I was saying, are labeled by the 4 possible algebra objects that you can have in the input fusion category, which is S3. And notice that this is all consistent because using the SIMTFT, we argue that asymmetric TQFTs corresponds to choices of the physical boundary conditions. And essentially, the algebra object that you need to pick to realize that particular TQFT corresponding to this boundary is exactly the Frobenius algebra object that realizes this boundary by performing the appropriate gauging of the input fusion category. So this is the correspondence. And since this anion chain actually admits a tensor product Hilbert space, we can rewrite this in a more familiar standard spin chain Hamiltonian way. And this has some related work with Rapestri symmetry has also been done here by Louise and Paul that are in the audience, and also people in the audience here with this paper that came out with ours. And the idea is that we can write this generalized Ising Hamiltonian that depends on two parameters, lambda and t. And the particular form is not very insightful of this P and X operator, but the important thing is that they can be written in terms of standard sigma X and sigma Z polymatrices acting on the qubits, and standard or generalized polymatrices Z and X acting on the qubits. So P is an operator centered on the qubits, while X is centered on the qubits. And by tuning these parameters, lambda and t, we can actually write down 4 fixed point Hamiltonians that realize each of the phases I discussed using the MTFT. So the ground states of this Hamiltonian completely reproduce the continuum results. And as expected, we know that this should come from some sort of Rapestri symmetry. And indeed, we can write explicitly PNE lattice operators that commute with this Hamiltonian, and that explain this ground state degeneracy that we obtain. And we can also study phase transitions, and we do the simplest 1 parameter lambda interpolation between 2 fixed point Hamiltonians, H1 and Hj, that describe the, let's say, a gapped phase I and a gapped phase A. And then we know that, for example, tuning lambda at 1 alpha, we should reproduce the CFT at the phase transition. And doing this, we observe, for example, the Ising CFT at the transition between the trivial phase and the Z2SSB phase, the 3-state Potts model at the transition between the trivial phase and the Rapestri mod Z2 phase, and this slightly more exotic Ising plus Ising CFT at this phase transition. Okay, so to conclude, we have seen that we can use the SIMTFT to have a powerful machinery that studies gapped and gapless phases in 1+1D. This is a framework that is very general because it's applicable to any fusion category S, and that we can also construct very concretely lattice models that provide a UV realization of this paradigm. And as the future direction, of course, it would be interesting to is beyond 1+1D because this is very, or that as I was quite restricted to 2 dimensions, and also maybe possibly experimental realizations of these lattice models that involve more exotic symmetries. And okay, with this I conclude. Thank you.
Thanks very much. So does anyone have any questions for Lea?
So you described the theories that live in the phase transition between these phases, but do you know if I have one such symmetry and I have different vacua, how can I have a domain wall theory between this vacua and what it would look like or something?
Like you're asking about actual theory living on the domain wall between the vacua. We didn't study that, so I'm not sure.
Another question.
Maybe just to clarify a little bit, so in the lattice model you provided, there is some data. The rho, you say, is an object in the fusion category C. So what is its relation with this M? Do you have this M always equal to the category of modules or this rho?
No, so basically you take an input fusion category C, and rho has to be an object in this input fusion category. And then M has to be any C module category that you want. So in particular, for example, you always have the regular module category, which is C itself. In this case, everything in this diagram will be labeled by elements in the input fusion category. But you can also, in some cases where C is non-anomalous, for example, you can have M equal vec. In this case, this will have only one trivial object, and then rho would still be labeled by any object you want in the input fusion category C. Depending on the choice of rho, you will have different models.
So they are like 2 degrees of freedom you can...
Yes.
Thanks.
May I ask a question?
I thought you would, like, if you choose one module category, you always have like a algebra which is natural, which is the one that gives you the module by the internal home, no? That's what gives you the phase. Right? That's what you choose in the talk for rho.
But yeah, I mean, I generically pick rho to be the sum of all elements. This is just to define the state space of the model. And then if I want to construct actually a gapped Hamiltonian, this is specified by an algebra object.
Which is the one.
But then it means that like when you glue this Hamiltonian on top of this fusion tree, this will only be gluable on things that are labeled by actually algebra objects and not a generic object. So in the end, you end up when you act with a gapped Hamiltonian, you end up producing.
But the algebra depends on the choice of M, no? You can...
Yeah. No, like the algebra object is always in the input fusion category. M just tells you what's the symmetry that you have because S is given by C dual M.
Okay.
But it's like saying that the gap boundary conditions of S3 and rep S3 are the same because the dream force center is the same, but then the interpretation is different. So here we always have the same algebra object in the input fusion category, but then depending on M, the symmetry S actually acting on the model is different.
Like M will give you the ground states of the TFT in the IR, no? The model category.
Yeah, I mean, depending on the gapped Hamiltonian.
Okay.
Time for one last question.
Hi. Can you characterize some properties of the CFT that separate the 2 phases?
In using this picture here?
Yes, like the symmetries of this CFT or a part of...
Yeah, it's a bit of weird question what actually this machinery produces to the input CFT that you have. But it's, I mean, this is not a setup that given 2 arbitrary gapped phases can tell you what's the CFT, CTIC, and the transition, right? So it can tell you once you have like if you have a phase transition for a small symmetry, let's say a Z2 symmetric CFT, then you can use it to upgrade it to a CFT for a larger symmetry. So like all the properties that this CFT have is basically the property of the input CFT, but it's always stacked with some topological order on top that actually enlarges the symmetry. So I mean, you know the symmetry which is S, but then the rest of the property of the CFT are the property of the input one that you feed to the construction.
So I suggest further questions to defer to the lunch break. Let's thank Lea again for that very nice talk.